All right, so getting on to the meat of today's lesson. All right, and I've probably got about 20 minutes or so of talking to go through. So, electron configuration and the Schrodinger model of the atom. All right, okay, and so what you need to know is how we actually use this model. All right, now there's a very helpful thing for you to be aware of, and that is where the different shells, subshells, line up on the periodic table. And so one of the things just here that is quite helpful to know is all of our S subshells are found here. All of our P subshells are found there. So we've got our S, we've got our P, and then of course our transition metals just here. These are our D subshells. Then you have your F subshell with your lanthanides and actinides down the bottom. Okay. What's actually going on is that effectively in the periodic table, okay, each row, so each period is a energy shell of electrons, okay? And that works out perfectly until you get to the third and fourth shell when your D block suborbitals start to overlap with your 4s suborbital. So your 3D and your 4s, they start to overlap and you start to get electrons that have very, very similar energy. And when you start having an overlap, what that just means is that atoms have some extra options when it comes to how they can arrange their electrons. And by having extra options, that means that they can do slightly more complicated things like form ions with different charges. Okay, so this will become how things like how copper has copper +1 and copper +2 will become a little bit clearer once you have an understanding of this model. Okay, but again, sounds very complicated the first time you're hearing it, but when you actually know what you got to do to actually apply it, you realize that it's really just using the periodic table as a map. Okay, and then knowing how to use that map to be able to work out the basically the shorthand code for saying where electrons are found in the element or the atom of the element. All right, and then using that to actually go, okay, there's been a change. All right, where is that electron gone? Okay, so if we take a little look just here, I figured we'll start with a couple of examples just here. All right. Okay, and so these are we've got two elements, boron and carbon. Okay, and I wanted to show you how we would use the periodic table. And so what I have pictured up on the left-hand side here is that slightly different version of the periodic table, which has the SPDF notations on it. And I also just grabbed the basically a view of boron and carbon just from the NESA periodic table. Okay. All right. So if we take a look here, all right. So we go boron. If we were just to take a little look here. So in terms of protons, it's got 5 protons. In terms of electrons, it's got 5 of them. Okay. And in terms of neutrons, on average, it's going to have at least 6. Okay, but because it's 10.81, it means that there are some other isotopes that have a different number of neutrons. Now, we need to worry about those 5 electrons though. Okay, so counting up, if we just take a look here, so it's the 5th atom. So we have 1, we have 2, we have 3, 4, and 5. That is where boron is found. Okay, so in terms of writing the electron configuration in terms of SPDF notation, we write our first shell, so 1s. All right, there's 2 electrons found in it. Okay, so we write 1s2. All right, we have electrons in our 2s shell. So we write that down, and they're both filled. So we write our 2 just there. And we have an one electron in our 2p. So we have our 2p, and there's only one electron. All right, so what this means, people, and I'm just going to switch colors just here. All right, is that in terms of representing where the electrons are found around that nucleus, okay, here we have our energy shell. It's a terrible H. All right, so it's that and that. The number out the front is our energy shell. Okay, I'm going to swap colors again. Let's go with green. All right. Our letter codes here, all right, they're our subshells that are found in each of our shells. Okay, and I'm going to swap colors once again. Let's go with purple this time. All right, and then each of these numbers here, okay, that's our number of electrons in each subshell. All right, so the big thing just to take note here is that what this actually gives us is it gives us a slightly more complicated view of the atom, in that it tells us exactly where electrons can be found surrounding that nucleus. Okay. All right, and of course the outermost electrons are the electrons that are found in the outermost shell, which is the second shell. So our 2s and our 2p electrons are available to actually be transferred or shared with another atom, in the case of boron. Now, if we take a look at carbon just here, all right, carbon is the 6th element. Okay, so that means it's found just here. All right, so that's our boron here, and then we have our carbon just here. All right, so again, the way we go from here, we count from hydrogen. All right, how many? So we have a 1s subshell, okay? But in the case of carbon, because you have 6 electrons, that subshell is full. So there are 2 electrons found in here. Now, in the case, we go to our next part of the periodic table. All right, so starting at lithium, all right, we have our 2s subshell. That is also full. All right. And then we count up to carbon, which means we have a 2p subshell. But because there is only 2 electrons found in there, we have only a 2 here. All right. And that gives us our way of saying where electrons are actually found surrounding the nucleus. And effectively, when it comes to working with the type of questions you're going to get, in most cases, it'll be, you know, this is a write down the electron configuration or the SPDF in SPDF notation for the following atom, or a multiple choice question where it says which of the following notations is the correct one for this atom or ion. Okay. All right. So that's what we're looking at. I'm just going to clear these and we'll just move on to the next part. All right. Okay. So the other thing to take a look at is when you actually have your notations, okay? So when you actually have them, all right, what you can do is you can actually go to the individual electrons, all right? Okay, and you can start to work out where surrounding the nucleus they're found. And so often the easiest way to do that is to draw a series of boxes. So we take a look at boron, okay? Again, just using the notation just here that we just worked out. We have 2 electrons in our 1s orbital. All right, so what that's going to look like is we'll have 1 up arrow, we'll have 1 down arrow. All right, in our 2s orbital, we'll have, again, one up arrow and one down arrow. And our single electron, that's the upper number just here, that is found in our p orbital, we're going to have a single up. Okay. All right. And that's kind of gives us an idea of the 5 electrons surrounding boron, okay, in terms of where they're located. All right. And because we know the shapes of these orbitals, so we know that basically we have a spherical electron cloud, all right, in terms of the 1s orbital surrounding that nucleus. Then like a Russian doll, we have a 2s orbital surrounding that first one. And then we have part of the teardrop of the 2p, okay, surrounding that nucleus as well. All righty. Now, let's take a look at our second one, our carbon just here, because this is where we start to see some of our other rules about working with these, this notation come into play. Okay, so again, we have 2 1s electrons. So that means we have an up and a down arrow filling that orbital. All right, we have 2 2s ones. So we have an up and a down arrow filling that orbital. And now we have 2 electrons in the 2p subshells. Okay, or orbitals that in the 2p subshell. All right, now one of the things I want to point out just here, and this is one of the traps we will try and trap you on when it comes to a chemistry exam, is that it's so easy to go, oh, there's 2 electrons, one's up, one's down, but you'd be incorrect. All right, and that's because of Hund's rule. All right, what will happen is the second electron will actually fill a second orbital. All right, and what will happen as you keep going up with more and more electrons, okay, is that you would the next electron would go here, and then if we add another electron, it would go there. But in the case of carbon, that'll be the correct arrangement of electrons surrounding its nucleus.
So,
okay. Yep.
Are there only like 3 p boxes, or are there more?
Well, there are a total of 3 orbitals found within the p subshell. All right, but there is a p subshell in the second shell, third shell, fourth shell, fifth shell.
Okay.
But there's not one in the first shell. Okay, there's only an S subshell in the first shell. All right, so again, this is really, it's just kind of, it's showing how that shape of the periodic table actually tells us a lot of detail. All right, it's one of those things I've often said to my chemistry students in the past. You know how to properly read the periodic table. About 40% of the answers in the exam can be read straight off the periodic table. Okay, so it's just one of those things. The amount of information we send to you on a single page that is just given to you for the exam is absolutely massive. You need to know how to read it. You need to know how to use it. Okay, so I'm just going to clear this. And all right, now there's another thing just to kind of be mindful of, and that is when you start getting overlap. Okay, and this is where what happens is scientists will start to throw out basically a diagram like this just here. Let's get rid of that. Okay, all right, and this is a an orbital filling diagram. Okay, now the basics of how this actually works is it tells you that your 1s orbital is filled before your 2s orbital, which is then filled before your 2p, which is filled before your 3s, then your 4s, your 3p. All right, and then your 3d, 4p, and so forth. Okay, in most cases, what I will point out, it's actually really straightforward to draw this. Okay, that's a little bit more of a complicated version of the diagram. So we've got your 1s, your 2s, your 3s. You've got your 2p. Oh, 1 second. So you've got your 2p, you've got your 3p, you've got your 3d. I'm only drawing part of it just here, but basically what happens, I'll just switch colors, is that in terms of how these are filled, is you just draw diagonal lines. Okay. So what happens is we fill first our 1s, then our 2s, then our 2p and 3s, and then our 3p, and eventually I haven't drawn it down here, our 4s, and then our 3d. Okay, and so it's a very straightforward way to actually just draw one of these to work out the filling. All right, the same token, if you know about the Bohr model, you know that you have the 3D subshell. The transition metal electrons are filled after the fourth shell starts to fill, but they're actually part of the third shell. Okay, and again, you can see that when you look at the energy levels of those shells. All right, 3 and 4 start to overlap each other. And likewise, 4 and 5 overlap each other, and 5 and 6 overlap each other. All right, as there is more room around the nucleus and more possible arrangements of electrons. Okay, so this is just kind of, it's a helpful diagram to have. Now I'm just going to get rid of that. And I'm just going to clear that off just here. All right. Now, there is one kind of exception that happens when you have the transition metals. All right. And this actually goes a long way to explain why you get some elements in the transition metal block that have a whole bunch of different ions they can form, because they have a whole bunch of different ways that they can rearrange their electrons. So let me just draw that for you, just to show that to you. Okay, so if we take a look at chromium and copper, and so just to point out, okay, we're not showing. We're not showing the 1s, 2s, 2p. We're just not showing them, okay? Because I just don't want to spend the time drawing them. All right, so if we take a look at, say, chromium, for example. All right, and give me 1 second because I have just stuffed something up, people. Just going to get rid of that. All right, that's a D there. There we go. All right, so what we're actually concerned about, people, is we're concerned about breaking everything at the moment. Here we go, it should be back in business. All right, what we're actually concerned about is our 3D and 4S subshells. Okay. All right, and for those of you who are cluey, you'll notice that what's actually going on is that chromium is the fourth element across the transition block, and copper is the 9th element across the transition metal block. And so if we were to follow the rules for filling these, okay, if we take a look at chromium, okay, what you would do, okay, is if you filled it straight from the get-go, you would start with first your 4S gets filled before your 3D, okay? And so we have our 2 electrons just here. And then our 3D, we would have 4 electrons in one in each in a separate orbital. All right. Now, as it happens, atoms actually always try and find the lowest energy. Okay. And so let me just get the eraser. What actually happens is instead of having the 2 electrons in that orbital, okay, the electron jumps out of the 4s orbital, okay, and actually goes across to the D block. And so that lets this element have, chromium, have 6 electrons across its 3D and 4s subshells, all with an electron in a single orbital instead of having 2 in a single orbital. And that is actually lower energy than the first situation where you would have the second electron just there. All right. Now, in the case of copper, all right, so following through with that idea just here, I'm just going to clear it off and I'll just do it again. The idea that is going on. Okay, and remember our earlier subshells, we're just not drawing them just to keep this as simple as possible. All right, let me just, so we start with our 4s subshell is going to fill first. And so we have the 2 of them. Okay. And then we have 9 electrons. So remember Hund's rule. So these are going to fill one at a time. Okay. All right. And then, of course, we're going to start filling in our second electron. All right. Now, at this stage just here, it is more energetically favorable to have your D block with a full set of paired electrons than it is to have one unpaired electron and have your S block with a paired set of electrons. Okay, so in the case of copper, what happens is that electron from the S block actually goes across to the D block so that we have a full D block shell. Okay, and so they're the 2 exceptions. They happen for chromium and copper and every element below them in the transition metal block. Okay, likewise, there are similar exceptions halfway through the F block. Okay, all right, but they're things that you won't have to worry about. All right, in high school. And I don't even think they ever came up at university when I was studying chemistry either. All right, because they're not really an interesting answer. Okay, but so just to kind of give you an idea just here, what's going on, the reason why the transition metal block is so wild is because we have so many orbitals, there are a couple of possible arrangements that are stable. Okay, and the most stable arrangement of electrons is always going to be in such a way to have full subshells, so with at least one electron in every orbital. Okay, that's how the exceptions work. Alrighty, let me just get rid of the annotation tools. Alrighty, now we're going to finish on today with just some challenges. Now these are challenges for you to do. What I wanted to show you is how you could actually find the answers for these before we go. Okay, so just going to ptable.com. If, let's say, for example, you had to draw the notation for magnesium. Okay, all right. Now the nuclear notation can be found just here. Okay, all right. So you can actually double check for each of these elements the different notations that are present. Okay. All right. So let me just get rid of my annotations just here. All right. And we'll just head back here. And I figured we could do the first one as a worked example. All right. And then what I would do is I'd leave you lot to your own devices and we'll come back on Thursday and we'll go through each of these answers before we continue with breaking down what the holidays are going to look like. Okay. So if we take a look at argon. All right. Okay. Now in the case of argon, we have 18 electrons, I believe. Yes, 18 electrons. Okay. All right, so if we were to carry this across, and I'm just going to bring our annotations back. All right, so we've got 18 electrons. All right, so our 1s shell is full. Okay, so we have 1s2. Our 2s shell is also full. 2s2. Our 2p shell is also going to be full. All right, so that's 2p6. All right, and that, because argon with 18 electrons, all right, it's going to be, argon's actually going to be down here. Okay, so this means our 3s is going to be full, and our 3p is also going to be full. That's where argon's found. All right, now I want to actually also just show you another little trick as well. Okay, just before we wrap up, there's another way of writing these long electron configurations. Okay, but what we'll do is we're going to use calcium as an example because it's the next one up from argon. And calcium can be found, should be just here. All right, so if we take a look here, calcium is going to have 1s2, 2s2, 2p6, 3s2, and 3p6, because it's got the same electrons that are filled up orbitals as argon, but there's two more. So our 4s shells just here. All right, so 4s2. So that would be one way of writing this, okay? But one of the things that is very handy to know, chemists, we love how shorthand, okay? So notice that this section just here is identical to this section just here, okay? So another way of writing this down would be to go and write argon, which is just a shorthand for saying the electron configuration of argon, then going 4s2. All right, much simpler way of writing down the configuration of calcium. So it's something you can do as you go and you look at the bigger elements. It makes your life a little bit easier because it saves you from having to write down the long configuration. Okay. All right, so what I'll say we're going to do right now is we're going to go into question and answer just at the moment. All right, and I'll leave the remaining 4 questions for you to complete.